Welcome to the Math Record. Today I'll be covering related rates. So basically in our videos thus far, I've been using the derivative to calculate for slope or like other things about graphs. What I want to do in this video is that we're going to have a more practical sense of the derivative and how to like solve like somewhat like real world questions using just derivatives, finding derivatives. So one of the most common questions with related rates is with cars. So basically, let's say we have a car that's at the position 0, 0, and it's moving north at 12 miles per hour. And let's say we have another car that's at 10, 0, and it's moving west at 5 miles per hour. So the question is, what is the rate at which the distance is changing at time 1 hour? Well, to solve this, let's draw a picture. And also just a warning, to solve these questions, you're going to have to understand implicit differentiation. So if you didn't understand that, go back to my video on implicit differentiation, which I believe was one of the last few videos for chapter 1. Okay, so we have a coordinate and we have a car at 0, 0, and we're moving north at 12 miles per hour. And we have a car at 10, 0, and it's moving west, so it's moving this way at 5 miles per hour. So what happens at 1 hour? Well, at 1 hour, this car is right here. At 1 hour, the car is right here. So when we find the distance at that point, we have this line. But the question isn't asking about the distance. We're asking about the rate of the distance changing. So how do we find that? Well, we're going to use the derivative. So what we could use to find the derivative, we know that this is the distance. So let's call this value x and this value y. So we call that x squared plus y squared is equal to distance squared using the Pythagorean theorem. So to find the rate, we're going to have to do a derivative. So what do we do the derivative in respect to? Do we do it to x, y, or d? It's a trick question. We do it with respect to t. And the reason is because we're doing the rate at which the distance is changing as time changed to 1 hour. So we're doing it in respect to time. So d of dt. So d of dt of x squared plus d of dt of y squared and d of dt of d squared. So the derivative, as I said, implicit differentiation, if it's different variables, just do the derivative and then leave behind like the rate, basically. So the derivative of x squared is 2x, and then we leave behind dx over dt. Derivative of y squared is 2y, leave behind a dy over dt. And the derivative of d squared for dt is 2d times the rate at which the distance is changing in respect to time. And this is what we're looking for, the distance changing in respect to time, so the rate at which the distance is. Okay, so since all of them have 2, divide 2 on both sides, so it cancels out the 2. So we need to find x, the rate at which the x is changing, y, and the rate at which y is changing, and our distance. Okay, so first let's find x and y. Well, we know that this distance is 10 because it's at 10, 0. And we know in 1 hour, this car moves 5 miles per hour west. So that means that at this 10, it moves 5 this way, because in 1 hour it moves 5 miles per hour is 5 miles. So 10 minus 5 is 5. That means x is 5. Using the same idea with this car, is moving at 12 miles per hour and starts at 0. So 12 times 1, and it starts at 0, means that it's at 12. So using the Pythagorean theorem, 5 squared plus 12 squared equals, take the square root, equals your distance at that moment. If you use your calculator or you know your Pythagorean triples, it's just 13. So your distance here is 13, our x is 5, and our y is 12. What about our rates? dx over dt, dy over dt? Well, that's actually this. Miles per hour are the change in x in respect to time, and the change in y in respect to time. So, sorry, I mean change in y in respect to time and change in x in respect to time. Because east and west deals with x, and north and south deals with y. Okay, so is this actually, to be careful, this 5 is not actually 5, it's actually negative 5. And the reason is because you're going west. So in the coordinate system, when you're going north, it's positive. We're going to the right, it's positive. When you're going down, it's negative. And going to the left is negative. West is negative, so we're going negative, going at a negative rate. So it's going to be negative 5 plus 12 times the distance at which the y is changing. So the y is changing going up, right? So it's going at a positive direction. So that's 12. And then multiply to d, the distance at which the rate at which the distance is changing. So this is negative 25 plus 144 divided by the 13. This should come out as 119 over 13, and the units are in miles per hour. So that means the rate at which the distance is changing is at 119 over 13 miles per hour. Okay, so those are one of the main questions. Another main question that's used is with cones, in water in cones. So let's say we have a cone that has a radius of 3 inches and a height of 4 inches. And let's say that there is water in the cone, and this water is leaking out at a rate of 5 cubic inches per second. So the question is, what is the rate the radius is changing when the radius is equal to 1.5 inches? So when the radius is halfway, basically. So let's draw a cone and is leaking out. So we have like water in the cone and it's like slowly leaking out. So, and this is leaking out at 5 cubic inches per second. So to be careful, like similar to how I did with the car with West, this is actually going to be negative 5 because your water was initially inside your cone. So when it's leaking out, the water inside the cone is losing it. So when it's losing, it's negative. So because the water isn't coming out from nowhere, it's coming out from the cone. So you're losing something. You're not gaining something that's leaking out. So we have a dot. Our radius is 3 and our height is 4. So our new one, we're not gonna is not actually time now, it's actually our radius, which is 1.5. So radius and height for cones are always perpendicular. So basically there's gotta be a new height instead of 4 now. So how do we calculate this? Well, we need to know the ratio between because triangles for cones are similar. So basically the ratio stays the same. So the ratio of the radius divided by the height. So the radius is 3 and the height is 4. And the radius for this one is 1.5. And this height is now, let's use a difference variable, h naught. So it's height at that point. So we know that the ratio, let's simplify it, r is equal to 3/4 h. So that's our ratio. Now we need to find our specific height. So 3 divided by 2 is 1.5. So 4 divided by 2 is h naught. So that means 4 divided by 2 is 2. So that's our h naught. Okay, now how do we find the amount of water in the cone? Well, we just use the formula for volume. So volume is 1/3 pi radius squared times height. We know the ratio because we're dealing with two variables, but we only want to find out radius. So we need to cancel out this height. So we know the ratio between radius and height is this. So let's substitute that in. We want to cancel out h, so let's rewrite this equation a bit. And we'll call that 4/3 radius is equal to height. Substitute that into our equation. So we get 1/3 times 4/3, which is 4/9 pi, times radius squared times this radius, which makes radius cubed. Okay. Now our volume is changing because this is not volume of the, because this is just calculating some volume of water. So our volume of our water is changing per second. So we're doing it in respect to time again. So dt of v equals 4/9 pi r3, which should come out as the change in water is equal to 4/9 pi is a constant, so we just leave it. And the derivative and dt r3, take the derivative since it's different variable, implicit differentiation. So that's 3r squared times the dr dt. Okay, and that's it. So we're going to substitute it in. So 3r squared times dr dt. And that is what we're looking for, the rate at which the radius is changing. So dv over dt, we already know what this is. This is the water changing in the cone, which is -5 because it's getting leaked out. And then we have 4/9 times 3, which is just 4/3. And then we still have our pi. And then our radius squared. So the radius at that point was 1.5 times 1.5. So 1.5 is the same thing as 3/2. So 3/2 squared times dr over dt. So we have -5 times 3/4, 3 over 4 pi. So we're dividing -5 by this, and then we need to divide by this. So simplify that one on this side first so we don't get confused. So 3 squared is 9, 2 squared is 4, so 9/4 dr dt. So that's -5 times 3/4 pi times 4/9. Cancel out your 4, cancel out the 3 with the 9 with the 3 left over. So that gives us that our answer is -5/3 pi, which is equal to our dr dt. And the units for this is going to be in inches per second, because the radius is in inches and time is in seconds. So that means the radius is changing at a rate of -5 over 3 pi, which makes sense because the radius is decreasing. That's why it's negative. Well, thanks for watching, and in the next video, I'll be covering optimization.